At the back of your notes is a warm-up. Here's the solution to the warm-up with all of the work shown. I'll walk you through what I did. We had to find the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x for the following. The first example was f of x equals 2x. So I'm going to replace the x with x plus delta x. When I distribute, I'm left with 2x plus 2 delta x minus 2x divided by delta x. The 2x's cancel, the delta x's can cancel, so I'm left with 2, and that would be my slope, which makes sense because f of x would be a line with a slope of 2. For example 2, we have f of x equals x cubed plus 2x plus 3. When I substitute x plus delta x for the x, I get the limit as delta x approaches 0 of x plus delta x cubed plus 2 times x plus delta x plus 3 minus the quantity x cubed plus 2x plus 3. When I expand using Pascal's triangle, I get x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. Distributing the 2, I get 2x plus 2 delta x plus 3. Distributing the negative sign gives negative x cubed minus 2x minus 3. The 3 terms at the back, the x cubed, negative 2x minus 3, cancel with 3 terms throughout the beginning, the positive 3, the positive 2x, and the positive x cubed. After I cancel those, I factored out a delta x and canceled it, so I was left with 3x squared plus 3x delta x plus x squared plus 2. Substituting 0 for delta x, my final answer is 3x squared plus 2, so that would be the slope equation. For the third problem, for what values of a and b is g of x equals ax plus 2b when x is less than or equal to 0, x squared plus 3a minus b when x is greater than 0 but less than or equal to 2, and 3x minus 5 when x is greater than 2, continuous everywhere. So what happens here is the top 2 equations have to be equal when x equals 0, and the bottom 2 equations have to be equal when x equals 2. So I set up 2 equations. I said a times 0, because I replaced the x with 0, plus 2b equals 0 plus 3a minus b. Combining like terms and simplifying, I had 2b equals 3a minus b. Adding the b to the other side, I had 3b equals 3a, which means b equals a. For the bottom 2 equations, I have 4 plus 3a minus b equals 6 minus 5. Everywhere there was an x, I replaced it with a 2. Then, simplifying, I subtracted 4 from both sides, so I had 3a minus b equals negative 3. I replaced the b with the a from the other equation, where I found out that they were equivalent. So I had 3a minus a equals negative 3. Combining like terms, I had 2a equals negative 3. Dividing by 2, I found out that a was negative 3/2. Since a and b are equal, that means b is also negative 3/2. For today's lesson, we're going to talk about limits involving infinity and asymptotes in graphs. So our objectives are to determine infinite limits from the left and from the right, find and sketch the vertical asymptotes of the graph of a function, and determine limits as x approaches infinity or negative infinity. An infinite limit is a limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. So here I've written down the limit of f of x as x approaches c equals infinity or negative infinity. Now it's important to note that the equal sign does not mean that the limit exists. It just describes the behavior of the function when the values in its domain or range outgrow all finite bounds. So essentially, it tells how the limit fails to exist. So it tells you how the limit fails to exist by denoting the unbounded behavior of f of x as x approaches c. So for the following, we're going to graph them in our calculator and use them to evaluate the limit as x approaches infinity and negative infinity. So for the first example, 1 over x, if you graph it in your calculator, this is what you're going to get. As we look at this, as x approaches infinity means as we go to the right, what is the function doing? Well, as I go to the right, the function is getting closer and closer to 0. And as I go to the left, the same thing is happening. So the limit as x approaches positive or negative infinity of f of x would be 0. For the second example, this would look like a volcano, and the same thing happens. As I approach infinity or negative infinity, I'm going to approach 0. So here it's the same limit. The limit as x approaches positive or negative infinity of f of x is 0. The third graph looks similar to the first graph. So it has the same limits as x approaches infinity and negative infinity. So as I'm going to the left or the right, the graph is getting closer and closer to 0. So the limit as x approaches positive or negative infinity of f of x equals 0. So a line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches infinity is b or the limit as x approaches negative infinity is b. So really, this is just another way to define a horizontal asymptote. We have some properties of infinite limits that you may want to look over. So if one limit is infinity and the other is a number, if we add them together, the limit's going to be infinity. If we multiply them and the limit is positive, the limit with the actual number, then the product is going to be infinity. If we're multiplying and the number is negative, then the limit is going to be negative infinity. And if g of x is a number over infinity, so a number over infinity, that equals 0. So rational functions are my favorite because we learned how to find the asymptotes of these in Unit 1. So as I look at this, the degrees are the same in the numerator and denominator. So that means that the horizontal asymptote is 2/5. So that means the limit as x approaches positive or negative infinity of f of x will be 2/5. For example B, we have 9/2 because our highest exponent in the numerator and denominator is both 4. For C, this one's a little bit sneaky because I have the 1/3 on the outside. I'm going to do the same thing I normally do with looking at the ratio of the leading coefficients. So because my x squareds are the same degree, my limit would be 1/8 to the 1/3. Now, the 1/3 power is the same as the cube root of 1/8, which would be 1/2. For this one, because the degree of my denominator is higher than the degree of my numerator, that means the limit of the function inside would be 0. Now, the square root of 0 is 0, so that means the limit as x approaches infinity is just 0. Now we're going to look at some one-sided limits. So I want to find the limit as x approaches 1 from the left. If I were to substitute 1 into this equation, I would get -1/0, which tells me asymptote at +1. So my asymptote would be here. Now, I want to know what happens as x approaches 1 from the left. So to make this a little bit easier, I'm also going to find the horizontal asymptote. Because the bottom is a higher degree than the top, it's going to be right here at 0. Now, if I substitute 0, because that's a value to the left of my asymptote, in for x, I would get -1/-1 squared, which is -1. So I have a point at 0, -1. This graph must be bounded by the asymptote, so the only place it could go is right in that quadrant there, which means as I approach 1 from the left, my limit is -infinity because my graph is going down. Something similar happens in F. I would have an asymptote at 1. My degree of the numerator and denominator are over here. It's a little sneaky there at the back. It's x in both cases, but one is positive and one is negative, so their leading coefficient would give us a ratio of -1. I want to know what happens as x approaches 1 from the right, so I'm going to substitute 2 in for x. So I would have 2 + 2 over 1 - 2, so that'd be 4 over -1, which is -4. So -4 would be down here, which means that my graph has nowhere else to go except for in this quadrant to the bottom right. So as I'm approaching 1 from the right, I'm approaching negative infinity because my graph is going down. For G, if I substitute 4 into the equation, I would get 16 over 16 plus 16. So I'd get 16 over 32, which is 1/2. So in this case, the 4 is not an asymptote, so it doesn't cause any problem. We just substitute it in. For H, I have 3 minus 2 over 9. Once again, no issues with an asymptote. I just simplify my fraction. For I, take a minute and graph this in your calculator. When you graph it in your calculator, go ahead and pause me while you graph it in your calculator, you'll see it's a pretty strange looking graph. The part I'm interested in is the part to the left of 0. The part to the left of 0 kind of looks something similar to this. So as I look at that, the limit as x approaches 0 from the left is positive infinity. For J, if I were to substitute pi over 2 in for cosine of x, so negative 2 over cosine of pi over 2 would be negative 2 over 0, which is undefined. Really, this is the same thing as negative 2 secant of x. So I know that secant has asymptotes at pi over 2 and 3 pi over 2. So right in the middle of pi over 2 and 3 pi over 2 would be pi. If I were to find negative 2 over cosine of pi, cosine of pi is negative 1, so this would be negative 2 over negative 1, which is 2. So at pi, I have a point up at 2. These graphs look like these weird whooshes. So as x approaches pi over 2 from the right, my graph is going to approach infinity. For the next example, I'm going to use the function x squared minus 1 divided by 2x plus 4. The first thing I'm going to do is I'm going to set the denominator equal to 0 and solve, and find out that I have an asymptote at negative 2. Now, in this case, I have a slant asymptote, not a horizontal asymptote. To find the location of that slant asymptote, I'm going to do x squared plus 0x minus 1 divided by 2x plus 4. X squared divided by 2x would be 1/2 x. When I multiply, I get x squared plus 2x. I subtract and I get negative 2x, bring down the negative 1. Negative 2x divided by 2x would be negative 1. I can stop dividing here because I've gotten the equation of my line. So I have a y-intercept of 1, a slope of 1/2. So my graph looks something like this. If I choose a value to the right of negative 2, for example, negative 1, I would have 1 minus 1 over 6, which would give me 0. So I have this point at negative 1, 0. Now, once again, this graph has to be bounded by its asymptote, so really the only thing it can do is something kind of like this. And then the other piece is diagonally across from that one. So now, as I look at my graph, as x approaches negative 2 from the right, my graph is going up, so that means this one is infinity. As x approaches negative 2 from the left would be the other side, so that graph is approaching negative infinity. As x approaches 1, well, there's no problem at 1. I can just substitute it in for x. If I substitute it in for x, I get 0. And then over here, I want the limit as x approaches 0. Once again, 0 doesn't give me a problem if I just do straight substitution, so I get 1/4. Vertical asymptotes. If f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote of the graph of f. So the limit as x approaches a from the right would be positive or negative infinity, and the limit as x approaches a from the left would also be positive or negative infinity. So some review on finding vertical asymptotes here. This vertical asymptote would be located at x equals 2. Here, if I said x squared plus 4 equals 0, x squared equals negative 4, so I can't take the square root of a negative number and get a real answer. So this means there is no vertical asymptote. C will actually have 2. If I factor the bottom, I have s minus 5 times s plus 5. So that means my vertical asymptotes are located at s equals 5 and s equals negative 5. For G, it's already factored, so I can say x squared equals 0, 1 minus x equals 0, so 1 equals x, and then x equals 0. So that means I have asymptotes at these two locations, x equals 0, x equals 1. For E, before we can figure out where our asymptotes are located, we have to factor. The numerator factors into x plus 2 times x minus 2. The denominator I can factor by grouping. The GCF of the first pair is x squared, leaving me x plus 2. The GCF of the second pair would be 1, leaving me x plus 2. So I get x squared plus 1 times x plus 2. Now, when I compare that to the numerator, the x plus 2's cancel. X squared plus 1 equals 0 results in no vertical asymptote. For F, we're also going to factor, so I would have t times t minus 2. The bottom is t to the 4th minus 16, which is a difference of 2 squares. So it would start off as t squared minus 4 times t squared plus 4. T squared minus 4 is going to break down again into t plus 2 times t minus 2 times t squared plus 4. Canceling the t plus 2's, I will have a vertical asymptote left at t equals 2. So a lot of this is review from Unit 1, finding vertical and horizontal asymptotes. Please work on your homework and come see me if you have any questions.